Alright, welcome to today's lesson on entropy changes. You can see from this demonstration here, entropy is disorder. At the start we have a nice ordered entropy sign, but as we have some molecules moving around in our system, it's going to cause absolute chaos. There is only one way, or a few different ways, that we could arrange all of these molecules to make the word entropy, but there is a near infinite number of ways that these molecules can be arranged that they're not in this formation. They can be absolutely anywhere. That's why there's a rule of the universe that entropy must always be increasing. We give it the symbol delta S, this means change in enthalpy, and we give it the units joules per Kelvin per mole. So a joule is just a unit of energy, per Kelvin a unit of heat, per mole how many molecules we have. Cool. So what is entropy? It is the change in orderedness of a system. Different from change in enthalpy, which is just the change in heat of a system. Change in orderedness versus change of heat, they are related, but they're two very different concepts. And as you can see, how did all this messy stuff happen? It is just entropy. There's only one way that this stuff could be nice and ordered, but many different ways it can fall apart. So your room will always get messy over time, unless you put work in to reverse it. Here we have three different phases of matter, solid, liquid, and gas. Which of these phases of matter is the most disordered? Which has the most amount of possible states the system can exist in? Well, you're a solid, very few states it can exist in. It's all locked in one place. Liquid has a few more, but then gas absolutely has the most amount of states that a system can exist in, because a gas molecule can literally be anywhere, and this one could be up here, but another time this one could be down here. Many different ways it could be. Gases have the most entropy. So gases have the most entropy. Here is slightly different. We have NH3 reacting to go to N2 and hydrogen gas. Ammonia gas making nitrogen gas and hydrogen gas. Here, both the products and the reactants exist in the gas state. So are the products or reactants more disordered? We can't look at the state change. We have to look at the number of moles. We have 2 moles on this side of our equation and 4 moles over here. So 1 here and 3 here. That makes 4. We're going from 2 moles to 4 moles. There are more ways to arrange 4 moles of something than 2 moles, so our products are going to be more disordered. So there's an increase in entropy. The entropy with more moles is greater than the entropy of fewer moles. Dissolving a solid. When you dissolve a solid, first you go from a solid to an aqueous solution. Going from a solid to an aqueous solution means that there's more chaos and more disorder in there, so you're increasing entropy, but also you're breaking up the nice structure of the solid. All these solid particles are together. You're breaking up the structure of the liquid. All these liquid particles are together, and you're breaking them up. There's so many more ways you can arrange this system than you can arrange these two systems. So those are the 2 ways dissolving a solid increases entropy. I want you to think about this question for a bit. We have 2 moles of hydrogen gas reacting with 1 mole of oxygen gas, making 2 moles of liquid water. Is this reaction decreasing or increasing entropy? I'm going to pause the video, maybe write a couple of sentences in your book, or just have a think about it, and think about why this would be increasing or decreasing entropy. Alright, you should have had a little think about this now. On our product side, we have 3 moles. We have 2 moles of hydrogen gas and 1 mole of oxygen. That's 3 moles. On our product side, we only have 2 moles. So we're going from 3 moles of reactants to 2 moles of products. This is a decrease in entropy because we're going from 3 moles to 2 moles. Also, we're going from 3 moles of gas to 2 moles of liquid. This is making it more ordered. So in both cases, we're decreasing the number of moles and decreasing our orderedness of our state changes, going from a gas to a liquid, making the system more ordered. In this reaction, 3 moles of gas combine to produce 2 moles of liquid. There is a decrease in entropy as fewer moles are produced than what was started with. Liquid is a more ordered substance compared to a gas, therefore entropy is decreasing. Which breaks the second law of thermodynamics. The second law of thermodynamics states that entropy must always be increasing. That's not negotiable. Every single chemical reaction has to increase entropy. So what's happening here? Entropy, this reaction does actually happen, by the way. You can combine hydrogen, oxygen gas and mix water, and this is lots of combustion reactions. And combustion reactions release a lot of heat. So while entropy is decreasing, it's giving off a whole bunch of heat. When it gives off this heat in an exothermic reaction, we can tell it's exothermic because delta H is negative. Exothermic because delta H is negative. Surroundings heat up. When the surrounding air or liquid heats up, it has greater kinetic energy, meaning your surroundings heat up. They're moving around faster. Things are going to get more disordered. Your chemical equation is going to become more ordered, so entropy is decreasing. But the surroundings are going to have the entropy increasing. So that is why we haven't broken the law of thermodynamics. Because of this. This delta H is the key. This is how delta H actually links to entropy in the first place. It's an exothermic reaction, heating up the surroundings, increasing the entropy of the surroundings. This is a bit more of a complicated equation, and I'll show you this in class when we go back to school. Have a think if this is increasing or decreasing entropy. So we can see we have 3 moles of reactants going to 5 moles of products. Our reactants are both solids, while our products are gases and liquids. So we have more moles, which means it's more disordered, more increasing entropy, and going to a gas and a liquid, which is more disordered than solids, so increasing entropy. Cool. The second law of thermodynamics states that total entropy of a system can never decrease over time. The trick here is none of these systems are isolated. They're all linked together, so the surroundings heat up. Your freezer actually does this at home. If you think, how can you cool down something? If you cool down something, you're making it more ordered, so entropy is decreasing. Your freezer does this by actually heating up the surroundings. So your freezer can't just cool down without also heating something up. So something else heats up, which is the radiator coils at the back of the freezer, which is giving off heat, making the surroundings more disordered. Cool. The heat pump in the fridge does work to reduce the entropy inside it. This is reducing entropy, but the room heats up by a lot more than what your freezer cools down. These are the notes I want you to get down into your books for today, and try the Google Classroom task, which will be due on Tuesday night. All right, thank you guys.